So today I'll be talking about ICO protocols and token sale models. First, a couple of words about prerequisites. They're all listed, but don't feel discouraged if you don't have something that's listed there, because they are not necessary prerequisites but sufficient. So even if you haven't touched Solidity before, you should be able to read most of the code. And nothing from economics is going to require a PhD from you. So bear with me. A couple of words about implementations. I'm going to show examples in Solidity. In the end, there's going to be GitHub link to all of the examples and some useful links describing different protocols and different implementations. When I'll be discussing these contracts, I will omit the token logic. So we will just assume that the token can somehow send the newly minted tokens to the buyers. I'll have some basic contracts that our contract of interest inherits from, like ownable or posable. These are reference implementations from OpenZeppelin, which is a famous organization that creates reference implementations in Solidity code. The examples from them are going to be pretty self-explanatory, so they're easy to understand. And finally, the examples I've created are designed to be as simple as possible, to be easily understandable, but they're not really feature-rich. So if you need some specific features in your own contract, you can, for example, use my contract and add those features on top. But they work. So why should the smart contract developer know about economic properties of token sales and how these sales work? Well, for me personally, when I started in the DLT sphere, I was really excited about how this an intersection of numerous disciplines like computer science, cryptography, and economics and game theory. So for me, for example, that's the reason as good as any. But if you need to know how it will benefit you professionally, then if, for example, your company wants to do an ICO, you need to the token. Jesus. It's going to be hard to only concern yourself with just the token models, the economics separated from the code. Because the best token model will be chosen based on the project stakeholders and how it suits them. But then the model has to be implemented. So it's going to be your job to work closely with the business people to work out the kinks in the implementation. For example, you must be able to give argumentation why this or that part of the business model is not applicable in the smart contract, or if it's not reasonable. And it's your job to ensure that the smart contract matches the model and that the model doesn't get broken because of the discrepancies. A bit about how it all started. The first ICO known of is Mastercoin in 2013. It was a simple uncapped sale, which means you publish an address and you receive blockchain's native tokens onto it. Here it was a Bitcoin address, and the respective master coins were sent to Bitcoin users as well, because it was supposed to be an overlay network above Bitcoin. Then there was Ethereum, which also received funding in Bitcoins. Considering that Bitcoin doesn't support sophisticated coding possibilities, the models back then were quite simple. Also, a lot of crowd sales accepted different coins. However, this led to discrepancies due to different exchange rates, so it's not done anymore. So how would you implement an uncapped sale in Solidity? Here we have some attributes. There is the token interface attributes and other parameters. There is also a custom modifier, which controls whether an ICO is currently in process, just checking if the current block is between the start and the end. Then we have the constructor, basically just some assignments. The interesting one is only the token, because in Solidity you can just use an address to create a new variable of contract type. Then there is a function of bonus calculation, which is now a stub, but you can implement some logic specific to your own ICO to calculate the bonus, for example, based on the current timestamp or current block. And finally, there is a function to buy tokens, which the buyer calls. It just calculates the amount and sends it to the specified address using some token function. There is a fallback function. It's the one that is called when some money is sent to the contract, but no function is specified. So it's implemented to ensure that nobody can send money to the contract, and this money will just be gone without calling any function. And finally, there is a function to withdraw ether from the contract, the ether which was collected. And that is pretty much all. It's that easy. Let's analyze some of the properties of the uncapped sales. It's a very easy model. So these things, without some additional contracts like ownable or posable, or without the token logic, it's just 60 lines of code. And it's very simple for the investors because the participation is unlimited. So all you do is just send money. However, there's one major drawback because of which this model isn't used anymore, and that is uncertainty of valuation. More sophisticated investors will want to leverage the percentage of tokens they have. So, for example, they would be willing to pay $100,000 for 1% of the tokens. But here the tokens are created indefinitely, so they have no way of predicting the percentage that they will have. And this is bad. This means that the investors you attract onto your platform do not consider such things, though they're not really thoughtful investors, unless they, of course, like your project out of some fundamental considerations. Another weird property that these sales have is that they may indirectly lead to congestions due to some game theoretic properties. If you look at the Ethereum sale, we will see that there was a period from the start to some point in time where the price of a single Ether was smallest. And the optimal way for the investors to behave in such a situation is to wait until the end of this period to decide whether to invest or not. Well, it's pretty simple to show that this is a Nash equilibrium. So if a single investor makes the decision earlier, then they have no information because everybody decides later, and their position is worse. And if they buy later, then they lose a part of the bonus. So again, their position is worse. And this theoretical equilibrium is supported by evidence because in the Ethereum sale, the bulk of buying transactions were exactly at this moment when the bonus stage ended. So if the crowd sale is very popular, the network may not be able to process all of these transactions in this equilibrium fast enough, and this leads to congestion. And if there is no bonus period, then this equilibrium will be at the very end of the crowd sale, which you will not want if you're an organizer, because you will have no information on how much money you raise. So for some examples, it's pretty much every sale before 2016, when Ethereum first became workable, is an uncapped sale, because that's the only thing you can do in Bitcoin. Some of the interesting examples, for example, are DAO and Tezos. These are the examples another example why you don't have to do an uncapped sale, because in case of the failure, there is no upper limit for how much money is lost. DAO was hacked for 50 million, and Tezos got 400 million locked up to due some founder dispute. There is also an interesting example of NXT. They had a fixed token supply, and it was distributed proportionally among the investors, proportionally to their contributions. And now this model with modifications is used quite frequently. For example, we will see later that it's used in the EOS sale. So let's talk about a different model, the capped sale. The difference from uncapped is obviously that there's a limit to total amount of contributions. So it may be set in crypto or fiat, but if you want to use a fiat, you need some kind of an oracle to find the exchange rate. They have gotten popular after 2015 because they are much easier to do in Ethereum than Bitcoin. In capped sales, we don't have to change much from the uncapped sale to make it work. So basically, there is a new attribute, the max cap. There is a small change in the buy tokens function, which is a new check that checks whether the new contribution exceeds the maximal cap. And we also have to change the constructor to accommodate this new attribute. And those are all the changes that you have to make. The cap sales are also very simple, as we've seen. And the feature here is that the valuation is strictly defined. So the investors always know which percentage of tokens they have. Also, they are incentivized to enter the crowd sale early because otherwise they may simply be too late. However, there also comes the main problem, that the army of investors trying to get in may pretty much stop the network in its tracks with all of their transactions. One of the most severe examples is Basic Attention Token. It was a 35 million crowd sale. about 135 transactions were successful, while 10,000 failed. More than that, about 70 Ether, which at the time was something close to $15,000, were spent on fees. So the investors have started a fee auction to ensure that their transaction gets into a block, because that's how much interest there was about, around the crowd sale. The biggest fee was actually about $6,000. These fee auctions are a paradise for large-scale investors or whales, because they can push out smaller investors by setting humongous fees, and then your project will end up with the half a dozen token holders which can manipulate price all they want, and this is very bad for you as an event organizer. So we see that these simpler models are really bad, and that's why more sophisticated models have appeared. Uncapped sales are not really just towards investors, can indirectly lead to network congestions, and they may be even a deal breaker for the regulator, because regulators do not like when there is no target cap for a fundraiser. At the same time, capped sales promote gold rush and fear of missing out mentality, and this leads to oversubscription, fee wars, and network congestion. However, the failures of these models have sparked a lot of interest in innovation in the token sale models and a lot of new research. So now we're going to discuss one more major model that is becoming more and more popular and is used in several crowd sales already. Then we will talk about some exotic modifications that you can see here or there in different crowd sales, and some of the state-of-the-art that is very promising but haven't been used yet. So without further ado, we will proceed to the reverse Dutch auction. The idea here is that it's a capped crowd sale model, but it has a twist. In the reverse Dutch auction, we have a fixed cap. So for example, it may be $10 million or 10,000 Ether. But the percentage of tokens purchased with that cap increases over time. So for example, it starts at 5% and grows to 95% by the end of the sale. Let's first look at the implementation, then I will discuss the economic properties. The new attributes for us are BP per block, which means basis points per block. A basis point is just 0.01%. And that's how much the percentage of tokens sold grows per block. Then we will also define a mapping between bidder addresses and their bids. We will need it later to calculate how much each bidder bought. And we also need a new modifier only after sale, which will allow us to honestly calculate how much tokens each bidder bought. Nothing new in the constructor, but the buy tokens function is replaced by the make bid function. And instead of sending the tokens to the buyer right away, we instead just write the bid into a memory, because we have to calculate all of this later. If the maximal cap is reached, then the crowd sale is ended by setting the end block to the current block. Now the bidder withdraws their earned tokens in a separate function, because it has to be done in the end, obviously, but also because doing this automatically at the end of the crowd sale is not constant from the amount of bids, so it may exceed the block gas limit in the Ethereum, and the transaction may simply get stuck, and the entire crowd sale gets stuck as a result. The function for the organizer withdrawal is pretty much the same. And there is a fallback function, obviously, that calls make bid, but I have not displayed it here. So let's now discuss the economic aspects. I have a model of Gnosis sale here for a visual example. The mechanism of reverse Dutch auction facilitates a strategy at which the investors waits until some moment t with a maximum valuation that satisfies him and then makes a bid. So if the crowd sale reaches that moment, then the investor gets makes a bid and gets at worst the same amount of tokens that they would get at the time t, but probably more, because the crowd sale still continues. And if the crowd sale doesn't reach it, then the investor can just opt out of a deal that doesn't satisfy them anyway. The cleverest thing about this model is how it approaches the uncertainty of participation. It doesn't solve this uncertainty directly, but rather gives investors more market information, allowing them to make a more thoughtful decision on whether to invest or not. So if an investor could not participate before the end, it's not as big a problem as it would be for them in a usual capped sale. And this model can also achieve a more fair distribution of tokens by leveraging the remaining part of the supply. For example, if some whale decides to block other investors from an ICO and buys out the cap themselves early, like the 5% of the tokens, then the remainder of the tokens, which is obviously very big, will return to the team, and then they can put it to different market makers. They can airdrop them to every Ethereum address, or they can sell this amount in the next round. Also, Ignosis sale is an important example because it was the first reverse Dutch auction sale, and it's important because it shows how even the smallest changes to your model can produce a very unexpected reaction. A couple of weeks before the sale, after Gnosis announced their sales structure, a lot of their followers expressed concern about the team retaining the tokens that were not sold. And it was a valid concern, as the team would have a central bank authority if the sale ended quickly. So the Gnosis team has decided to lock 90% of the tokens for a year, 90% of unsold tokens. What happened then is interesting. The sale itself ended in the first day with about 5% of total tokens sold, which gave Gnosis a gigantic valuation of about 250 million. This could be a very strong argument that the market players were being irrational and not having an optimal valuation in mind at all. However, if we turn away from the total cap and instead analyze the result in the short run, we see that the buyers were actually rational. On the graph, you can see the dependence of tokens in circulation before the end of 1-year lockup from a fraction in total tokens sold. We see that the short-run valuation, which is sold tokens plus 10% of the unsold tokens, grows much faster with time than the percentage of total tokens sold. So in the short run, the value of sold tokens was actually closer to 33%, and it's a quite normal value. And Vitalik Buterin, in his analysis, further argues that the investors were rational even in the long run, because for the Gnosis team, it only makes sense to release additional 90% of the tokens into the market if they believe that the price is going to go up. So these tokens are not harmful even after 1 year. So let's now discuss the lesser mechanisms. They are not separate token sale models, but they can be mixed and matched with different models to produce some interesting results. So I will introduce them shortly and then discuss each of them in detail. The first one is proportional refund. It's a capped sale, but instead of stopping the crowd sale at reaching the cap, you continue to accept contributions, and after the sale, divide the supply among the investors proportionally to their contributions, while at the same time refunding the over-contributed amount. Hidden caps are pretty self-explanatory. The sale is seemingly uncapped, but there is a hidden cap that is manually revealed at some point. You can either just directly reject contributions over this hidden cap or combine this with proportional refund. So in multi-round sales, instead of having one big crowd sale, you just organize several crowd sale rounds with smaller caps. And uncapped with fixed supply, it's just pretty much the same thing as proportional refund, but without the refund. And it's the model that was used in an NXT sale, as I mentioned before. So let's talk about proportional refund. It's pretty straightforward. You accept all contributions, but even over the cap. Then, in the end, the proportion of total amount raised that is over-contributed is calculated, and this fraction of each contribution is returned to the contributor. This type of sale sacrifices some certainty of valuation to allow everybody to partially participate. Now, an investor can be sure that they will get some amount of tokens at a fixed rate, but they cannot be sure which amount. And here it all comes down to the investor's personal utility functions. If their marginal utility is constant, meaning that 1% of the tokens for $100 is the same for them as 10% for $1,000, then it's all good, and this type of sale satisfies everybody. It's very good. But however, if the investor satisfaction grows faster than linearly with token percentage, then the value of the refund is not enough to counteract the utility loss. And unfortunately, practice shows that the second type of the investor is more frequent. However, you should still, when making this kind of crowd sale, research your investors to see if it will work or not. And on the other hand, this mechanism works brilliantly in the multi-round sales, as the refund allows the contributors to purchase more tokens in the next round. So their total utility after all rounds is much closer to optimal, even if they are second-type investors. To implement hidden caps, one needs to get some outside help, because in blockchain, all information is initially open. So to make the cap hidden, but also eliminate a possible attack vector from the organizer when they first say that the cap will be this, and then they just publish another cap onto the blockchain, we first publish a hash of cap value with some concatenated random string for additional security. And then when it's time to reveal the cap, the organizers publish the cap and the random string into the blockchain, and then it's trivial to check that the hash matches the published data. Here there may be a problem. If the ICO is oversubscribed, then the hidden cap reveal transaction may get stuck. So you have to safeguard against that happening and somehow track the order of transactions to remove the excess transactions, even if the hidden cap reveal was late. On its own, this model can be really strange, as it removes certainty of valuation. So you're actually better off not using it for a hard cap. But there may be some creative ways of using it. Like, for example, there was a project Aragon, which used it as a damage control method. So it was an uncapped sale, but they had a hidden cap to ensure that they don't raise very, very much, like much more than they ever need, and to attract attention from adversaries and hackers who could be interested in that kind of money. Also, it can be used to thwart whales to some extent. In your crowd sale, you can set a lot of hidden caps, which are not too far apart. And they are unlocked after some period of time, for example, daily. So this could partially solve inability to participate due to oversubscription or being pushed out by the whales. Because now the crowd sale is more stretched out in time, and it will be harder for a whale to suppress the rest of the network for this extended duration. Also, because these hidden caps are not so far apart, the whale will have to split their purchase, and that means that they will incur bigger transaction fees. So we've touched multi-round sales a bit already, and we can see that with other mechanisms, they're really good. They can vastly improve different models. Generally, multi-round sales make your crowd sales more resistant to whale attacks, as they have to sustain the attack longer and spend more money. They also increase the ability to participate in an obvious way. Now, another cool feature is that the multi-round sales can give investors an ability to better steer the project. So, for example, you can first host the first round for $1 million, and then the investors can see how the team progresses, how much they are successful with the project, and decide whether to invest in the next round or not. So big problem with a lot of ICOs was that you just do a crowd sale, and then you give the team, for example, 50 million, and then they have no incentive to keep working on the project. The only likely downside is that they introduce a lot of complexity, and with Solidity, as it is basically a financial system, this complexity may mean that it's easier to hack, and you may lose a lot of money. Finally, there is the last model, Uncapped with fixed supply. It's often used in multi-round sales. It seems pretty crazy as is, because it takes the worst parts of the proportional refund and throws away the advantages. But there's one interesting use case from the EOS crowd sale. So they've held one big round at first, and then waited for some time while the token was listed on the exchanges. So when the next rounds came, the token was already actively traded, and that allowed to have an effect of the crowd sale selling the token with the market price, because now the price fluctuates freely based on the amount of contributions. And if, for example, the last investor sees that it's already too expensive for him to buy the token during in the crowd sale, he can just go to the exchange and buy the tokens there. So the crowd sale price just converges to exchange price. The bad thing, though, here is that this introduces counterparty risks because exchanges are well known of just simulating the token turnover and manipulating token prices. So this is the final part. I'm going to tell you a bit about state-of-the-art things. There are, well, at least 3 models that I like very much. They may be a bit complex, so bear with me. First are interactive coin offerings. This is a fairly complex model that was proposed in autumn 2017 by Jason Toch, Vitalik Buterin, and Christopher Brown. Though it has some great game theoretic properties, it's pretty hard to code up, and that's why probably it wasn't implemented yet. The definition is as follows. The proposed model is an uncapped sale. It has 2 stages, arbitrary withdrawals and automatic withdrawals, separated by a withdrawal lock. So these stages are separated by rounds. During both stages, the contributors can submit a pair of a bid and a corresponding personal valuation cap. So during the first stage, users can withdraw their bids arbitrarily, but the part of the bid is locked permanently and a part of their bonus is slashed as a result. During the second stage, arbitrary withdrawals are no longer possible, but new bids can still be submitted. In this stage, the smart contract keeps track of the active bids with the minimal personal caps and partially or fully refunds these bids if the caps were exceeded by the valuation, basically throwing away these investors. So what are the properties of this sale model? The valuation doesn't decrease after any bid. That's why bids are refunded either fully or partially. It's attack resistant. There is no case where a rational adversary can get a bonus advantage by artificially inflating the valuation to keep other players out and then just withdrawing their bids and thus getting a bigger bonus. And that's why the partial bid lockdown and bonus penalty are implemented. It is resistant to veil pushouts as well, as it is stretched out in time. And the killer feature is that it allows contributors to not only react to actions of other players in deriving their personal strategy, but as the name suggests, it allows them to interact. So this pretty much makes uncertain valuation a non-problem, since each participant has much more information to decide their personal cap compared to a traditional sale. And in the end, all remaining participants are satisfied with the cap or with not participating in the sale. The problem is that the implementation is tricky. While all previously described models can be implemented with constant time functions, here automatically removing minimal cap bids requires maintaining some sorted data structures. And they are no longer constant time, and that may mean that the function may not execute because it exceeds the gas block limit in Ethereum. So it requires some very sophisticated tricks to counteract that. The only implementation as of now is the TrueBits library, which everybody can use to do a token sale, but no one yet has. Now I'm going to tell you about direct-to-market Dutch auction, which is a simple and interesting iteration on a normal Dutch auction. In this model, instead of raising the percentage of total tokens that is sold, the crowd sale releases equal-sized lots with exponentially dropping price. So the market price is discovered once some first lot is bought, but the lots with lower price are still released and will be bought below market price. However, these lots that are more expensive than market price still remain on the order book and can potentially be bought out. So the idea here is that these remaining orders will be bought out once and if token price of the exchanges will reach their level, which allows the developers to get a reward if the project is successful and the token is doing great. There may be some problems with gold rush mentality, as people try to buy out cheaper lots, but setting a proportional refund would pretty much be like setting a proportional refund in a multi-round sale, so this problem can be cured. Finally, there is a DAICO, a very recent proposal by Vitalik Buterin, which adds an element of a decentralized autonomous organization to an ICO. First, there is a funding round, which can use any arbitrary model or mechanism. But then the contract goes into the DAO stage, where the investors can vote on one or two actions, either to raise the so-called TAP, which is the amount of funds developers can withdraw from a contract per block, or to nullify the contract and proportionally refund the remaining ether to the investors. So this is a fairly simple model. The main advantage of this mechanism is that it largely neutralizes concerns on over-the-top valuation by implementing a more meritocratic approach. The investors can raise the TAP if the developers are successful in realizing the project, or they can cut funding altogether if the team is malicious. However, there is some nuance in specific components of the model. The used ICO model should be resistant to whale pushouts, or the entire affair will turn into some kind of unregulated private equity by function, because there are only 5 addresses that vote for different resolutions. Also, the voting system that Vitalik proposed is a stub. It simply counts votes from contributor addresses, so it is very susceptible to Sybil attacks, when you can make just a lot of addresses that contribute small amounts and then use them for votes. Vitalik argues that Sybil attacks are reversible as long as the voting and the team are not simultaneously malicious, but reverting them still consumes time and fees. So it's better to implement a more thoughtful voting system, like, for example, stake-based voting or quadratic voting. This is kind of out of scope of this discussion, but I still provided some links in the GitHub repository. So that's pretty much all I wanted to share. There is the promised GitHub link written, and also my contacts if you want any help with understanding this stuff or implementing it. So I'll give you time to write it down, and are there any questions? No questions.